My name is Ido Irani. I'm a PhD student with the Avishai Galiam group at the Weizmann Institute of Science in Israel. And I'd like to tell you a little bit about our recent work on the UV light curves of type 2 supernovae. So, of course, I invite you to read our full paper on, which is now on arXiv. So before I begin, just a little bit of background. So when a star explodes as a supernova, there is a shock that propagates outwards. This is the explosion itself, a shock propagating outwards inside the star. This is a radiation-mediated shock, so there are photons being emitted and captured in the shock transition layer. At some point, this shock transition layer reaches the edge of the star, and the shock will break out. So the photons that are being produced cannot be absorbed and continue the shock onwards. These photons escape to the observer, and this is what we call the shock breakout pulse. It lasts minutes to hours, and in some cases, it can also last maybe a day. Once this shock has broken out, we have a temperature and velocity gradient inside the ejecta that is now moving outwards. This ejecta is expanding and cooling, and we will be able to see this cooling in the described very nicely by models of the temperature and luminosity of the supernova, which will give us the model for how the supernova should evolve in the first few days as a function of progenitor properties like the progenitor radius and the energy of the explosion. So these are what we want to measure using supernovae. This shock cooling behavior is something that has been observed in the past, but has been also contested. So it's not clear if this has been really the case for the population. In some individual cases it works, in some other cases it doesn't work. We wanted to see if it works for type 2 supernovae as a population. What we did was to get early UV light curves for a sample of what we call infant supernovae. These are supernovae which we managed to catch very early after explosion. We see their rise very well in the optical bands from ZTF. And we managed to get there with the SWIFT UVOT instrument. SWIFT is a UV satellite, and UVOT is its UV instrument. As soon as 2 days, sometimes before, sometimes after, for many of the supernovae in our sample. On the right-hand side, you can see all of our data for a subset of the plot of the filters. So why do we need these UV light curves? We want to basically measure this temperature evolution. We want to see this cooling that I was talking about before. And to do this, we need to measure very hot temperatures where most of the light is emitted in the UV. So this is why we have to have early UV. And we did this. We fit the black body evolution of this sample. This is what you see on the right-hand side. The transparent curves that you see in the background are the evolution of individual supernovae, and the solid points and curves are the population mean. And the solid curve is the shock cooling model. So you see that as a population, the points follow this the behavior of these curves very well, which tells us that as a population, this describes the evolution of supernovae in the first few days. This is not true for all supernovae. There are some individual supernovae here. For example, this one supernova which is actually heating up and not cooling, and rising in luminosity. So some individual cases don't evolve according to this model. But for most supernovae, for 33 out of our 34 supernovae, they evolve according to shock cooling models. So we use these models and we fit the sample with these models to get the progenitor property. So primarily, we're interested in the progenitor radius. This is the radius where the shock has broken out. Tells us interesting things about the progenitor, about its CSM, that it ejected or didn't eject in the past year, in the last year before it exploded. And what you're seeing here is the progenitor radius distribution from the fit. So what we observed is this red histogram. This is the distribution, the posterior distribution of the breakout radius. See, it extends to very large radii that are much larger than this gray histogram, which is the observed small Magellanic Cloud and large Magellanic Cloud red supergiant radius distribution. So for a large fraction of our observed supernovae, we see that they have very large radii, which is indicative of a material that is ejected from the star just before it explodes. However, a lot of this is due to a luminosity bias. These larger breakout radii also give more luminous supernovae. So when we account for this, it actually shows us that a large fraction of supernovae are actually consistent, of exploding red supergiants are actually consistent with the radius distribution of observed red supergiants, with only about 30% of exploding red supergiants that have this dense mass loss. And this has implications for stellar models that are trying to explain what happens in the last year of the life of the supernova. So if you want to hear a little bit more about what this means, see our individual supernovae fits, understand what this means for future UV surveys, I invite you to read our paper. And thank you for having me.